Hey everybody, thanks for joining me. This is going to be a conversation about fats and lipids. Now, there's a couple of different classes of lipids, which is kind of lipids are a class of molecules that it's like a big umbrella term. Now, underneath that umbrella, there are things known as fatty acids. There are also things like cholesterol and vitamins like vitamin D. Now, what we're going to do today is kind of get a little bit of exposure to your fatty acids, cholesterol, and vitamin D. Now, vitamin D is just an example of a fat-soluble vitamin, um, but that's a good place to go. Okay, so with all that in mind, we've got about 11 slides that we're going to work through, and we get some of the stuff out of the way here, and I'll get the ball rolling. So, lipids and fats. Now, those two terms are not completely interchangeable, and I'm not sharing my screen yet, but I'm about to be. There we go. Lipids and fats. The term lipids is a term that is your bigger umbrella. Fats, I would say that the only reason that I would say it's not totally interchangeable with lipids is because of the fact that there's another type of molecule known as a fatty acid that is an example of a lipid. Now, we're going to work through this and I'll give you highlights of, things that are important to know about with respect to lipids and fats. But here we go. So, lipids are substances of biological origin that are soluble in organic solvents. So, the good thing is that we have a sense of what an organic molecule is. It's a molecule that's largely made up of carbons and hydrogens. Now, an organic solvent, okay, that word solvent, maybe you've heard that before. And a solvent is an example of like if you make Kool-Aid, water is the solvent for making that Kool-Aid. You took the Kool-Aid powder and you added water to that. The Kool-Aid powder dissolved in your water. So water is the solvent. Now, lipids, and maybe an example of a lipid that you're maybe familiar with would be something like, say, let's see, vegetable oil. Vegetable oil is a lipid that if you put that into water, what's going to happen? Well, it's going to cluster together. It's not going to mix up into that water. Now, with that in mind, um, that's the only reason really that I'm, hesitant to use lipids and fatty acids or lipids and fats interchangeably because an organic solvent would be something, like hexane or decane, any organic compound. Like if you got let's say if you got a solution of hexane and you added vegetable oil to that, that vegetable oil is going to mix up really well because that vegetable oil is a lipid and a lipid that is going to be soluble and it's going to mix up really well in an organic solvent. Now, lipids perform three major biological functions. One, lipids they can form what's known as a bilayer, and these are essential components of any biological membrane. So if you think about a cell, so a skin cell, a liver cell, any type of cell that makes up part of your body, I always kind of visualize them as like a sphere, basically. They have what's known as a lipid bilayer. So think about this as lipids form a bilayer, and those are your components of biological membrane. Lipids containing hydrocarbon side chains serve as energy stores. Now, this right here, this note is maybe an example of, if you know someone who's like an endurance athlete, or maybe they're involved in CrossFit or something like that. They do high intensity interval training or basically just really intense training in some form or fashion. They might be on a high fat low carb, HFLC, a high fat, low carb diet. What that means is they're getting most of their fuel, most of their body's energy from fat sources. So, you might see that in the form of, oh, well, I had breakfast of, 5 strips of bacon and 3 eggs. Well, their body is using all of those fats, and those fats have tons of energy. Now, the third component, or the third component is that lipids are involved in signaling events. So, what I mean by that is basically the way that one part of your body communicates with another part of your body, the way that, a skin cell communicates something to a liver cell, and a liver cell to a pancreas cell. Lipids mediate lots of those communications. So, you could say that, I guess, lipids serve a structural role. They serve as food, and they're communicators. Now, I want you to know those three roles and those three functions. Now, the ways that lipids are classified, there are a total of 5 major classes of lipids. There are fatty acids. Now, this is a specific type of compound that we're going to talk about. There are triacyl glycerols. There are glycerophospholipids. There are sphingolipids and steroids. Now, the three that we're going to focus on and discuss most in depth are our fatty acids, triacylglycerols, and our steroids. So those three are what we're going to talk about. Now, glycerophospholipids and sphingolipids, those are important to know about if you're taking a biochemistry class. But when we think about fatty acids, triacylglycerols, and steroids, there's kind of a connection to, your day-to-day life, or, when you get your annual physical, these things are relevant to you. Um, with that said, the first that we're going to dive into are our fatty acids. Now, on the right-hand side of the screen are a total of 3 different fatty acids. Those 3 fatty acids are, well, first of all, they have a total of 18 carbons. And I know that there's 18 carbons in part because, well, I can see that the number 18 is at the bottom of all of these molecules, and the number 1 is at the top of all of these molecules. Now, one thing that I want you to recognize about all of these compounds is this group right here. And it's always difficult and tricky to kind of like contort something in your mind. Like, I feel like I've seen that, but I don't know that I have. Well, this right here, or we've definitely seen it looking like this. That's known as a carboxylic acid. So when you hear fatty acid, the acid part of that name is coming from here, carboxylic acid. So we have on all of these molecules, we have a carboxylic acid here, 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 and then we have this, what's known as a hydrocarbon tail. Now, carboxylic acids, or fatty acids, are, simply put, they're carboxylic acids with long hydrocarbon chain side groups. Okay? So each one of those has a chain that's about 17 carbons long. Now, the predominant fatty acid residues in plants and animals are C16 and 18. What that means is that the most common fatty acids in plants and animals are 16 carbon and 18 carbons long. Now, saturated versus unsaturated. The nomenclature notation, okay? But before we get ahead of ourselves, what does that mean, saturated versus unsaturated? Now, I think the first context that I ever heard the word saturated in was probably whenever I was trying to clean up a spill. I spilled some water on the ground and I got a paper towel. I put that paper towel down, and before I knew it, that paper towel was saturated. That means that all of the water that it could possibly absorb, it had absorbed. I picked up my paper towel, the weight of it probably tripled, and there was still water on the ground. So all of the water that it could pick up, it had picked up. Now, when we talk about a saturated or an unsaturated fatty acid, what we're referencing is basically, does this molecule have double bonds or not? And whenever I say, does it have double bonds, I'm omitting this double bond right here. Instead, I'm looking at my hydrocarbon chain and I'm asking, is there a double bond there? Now, in the event that the chain has no double bonds, that is considered a saturated fatty acid. So I'm going to write sat. In the event that there are no double bonds, or sorry, there is at least one double bond, then I'm going to say that that is an unsaturated fatty acid. So I'm going to say that all three of these, let me extend unsaturated. Okay, so we've got a saturated fatty acid. The way that I always like to think about it is saturated with hydrogens. The reason that it's saturated with hydrogens is because if there aren't enough hydrogens, then you have to insert a double bond. You could also think about it as it's saturated with single bonds. So every place that there is a bond, it's a single bond. Okay, now the notation that we use, and this is an important point because you'll definitely see a question like this on an exam. The notation that we use is to write C to indicate carbon and then the number of total carbons. Now, all of these are C18 because there are a total of 18 carbons. Now, one thing that always throws people for a loop a little bit is they think, okay, you know, I kind of talked about the carboxylic acid and the chain as two separate things. Do I account for this carbon right here? Yes, you do. You account for that carbon in your counting of your total number of carbons. That carbon's labeled 1, this one's labeled 18. This molecule has 18 carbons. So this one on the far left-hand side has a common name of stearic acid. Stearic acid has a notation of C18 to indicate that it has 18 carbons, and then :0 to indicate that there are no double bonds. Now, whenever I see this C18:2, that's in reference to a fatty acid with 18 carbons, and that's right, two double bonds. Okay. Now, if we look at these different compounds, we say which one is our C18:2? Well, that would be none other than our linoleic acid. So then if we looked at this one, oleic acid, this is C18:1. Alpha linolenic acid is C18:1, 2, 3. Now, this next part, this is relevant to what we've talked about. And it's also something that you've probably heard about or maybe seen whenever you look at food packaging. All of the double bonds in naturally occurring fatty acids are in what's known as the cis configuration. We've talked about cis-trans isomers. So our naturally occurring fatty acids are in the cis configuration. Now, if the double bond is in the trans configuration, the significance of that is that molecule is going to be metabolized in a different way. And this is something that you've maybe heard about or seen on food labels because there are some foods out there that have trans fats. I know probably 15 years ago, there was not really a big controversy, but it was something that, well, trans fats they're not good for your health. And there were foods like McDonald's foods that, as it turns out, they had quite a few trans fats. And of course, then, there was always like a spirited debate where some people would be like, did you think that you were eating health food at McDonald's? And other people would say, no, I didn't. But if these are so detrimental, I definitely don't want to be eating them, or I want to at least know that I'm eating them. So, lots of big changes for lots of food producers. So all of our naturally occurring fatty acids are in the cis configuration. Now, the first double bond, whenever we're looking at any fatty acid, is generally between carbons number 9 and carbon number 10. Now, this numbering, well, this carboxylic acid is going to get carbon number 1 because it's referred to as being the highest priority. So the convention is that we're going to start from carbon number one, the carboxylic acid, and number off from there. So if we look at this, here we've got a double bond between carbon number 9 and 10. So that's where typically your first double bond is going to be. Then you're going to see a patterning of them. And you don't have to remember this terminology, but basically the pattern is double bond, followed by a single, followed by a single, followed by a double bond, in the event there are multiple. So here what we have is our first double bond, single, single, and then a double. So our second double bond there. Now, in polyunsaturated fatty acids, the double bonds are not conjugated. And that's the terminology you don't really have to be familiar with. Instead, I want you to know is the naturally occurring pattern of double, single, single, double. If it's double, single, double, that's not a naturally occurring fatty acid. If it's double, single, 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 double, that's also not a naturally occurring fatty acid, or that's maybe an oddball. Um, the convention is double, single, single, double. Okay, now this brought up the numbering of carbons, saturated versus unsaturated fatty acids. And now what we're going to get into is we are going to look at yes, we are going to look at maybe another term that you've probably been exposed to. And if you have someone who, if you know somebody who has, who is particularly concerned about their cardiovascular health, chances are they might eat a lot of fish. And one of the reasons that they eat a lot of fish is because fish has lots of, that was supposed to transition easily. They have lots of omega fatty acids. Now, omega fatty acids are pretty well known for having anti-inflammatory properties. Um, Now, with respect to that that terminology, omega fatty acids, the first thing that I want you to do is look at this molecule on the right-hand side. Now, what's maybe not super familiar to you that I'm going to make a modification of is, well, if you toggle back and forth between this fatty acid and this fatty acid, you'll know that your carboxylic acid is at the top here, but then it's a little bit different because it's actually COO minus, and it's at the bottom. I'm going to go ahead and draw this as COOH, and you could also think about this as, let me erase that, and, ooh, can I use, I think that I can do this. Yep, that's what I'm going to do, but I got to find my cursor. There we go. Okay. You might see a fatty acid that looks like this. Double bonded O and then OH. Okay. So we basically flipped it. Now, this is significant. The flipping itself is not significant, but whenever you hear that terminology like an omega-3 fatty acid, omega fatty acids are also known as N fatty acids. Now, if you've if you ever think about like the terminology that from like the Greek calendar, I think. Alpha and Omega. Alpha, or, some folks by their religious traditions talk about Alpha and Omega being like the beginning, Alpha, and Omega, the end. Now, that terminology is important for when we talk about omega fatty acids because our omega carbon is valuable for numbering off our omega fatty acids. So whenever you hear something like an omega-3 fatty acid, where is that 3 coming from? Well, the way that that is numbered is you are starting with the terminal or end carbon. So the one that's farthest from your carboxylic acid. So on these, it would be carbon number 18. Now, then what you're going to do is if you're talking about an omega-3 fatty acid, you're going to number from that 18th carbon and you're going to count up 3. So our 18th carbon would be 1, 2, and then we're going to put a double bond between those two carbons. Now, I'm going to draw a couple of these in just a minute because I think it's a little bit more clear whenever we draw them. Now, these, like I said, they're also known as omega, or sorry, also known as N fatty acids. For example, C16 colon 1, N minus 3, that's an example of a 16 carbon long fatty acid with a single double bond. And that double bond, or that is an example of an omega fatty acid. That double bond is found 3 from the end carbon there. We also have C colon 20, or C20 colon 5, N minus 3. That means that we've got 5 double bonds, and they begin 3 from the end and just kind of number off there. Now, like I said, I'm gonna draw some examples of these in just a little bit. But fatty acids um, form saturated fatty acids pack really tightly and form very rigid and organized aggregates. So what that means is if you have a bunch of saturated fatty acids, they're going to cluster together. They're going to pack really tightly. Now, I want to show you a image that I always like to look at. Not always, but I look at from time to time, and it kind of gives me an understanding of something. So on the left-hand side, or our middle image, which it kind of looks like a caterpillar, this is a saturated fatty acid. Notice how it basically makes a straight chain almost. Or, it's a zigzag line, but it's basically overall straight. Whereas our unsaturated fatty acid kind of has a dog leg to it, like a kick out to it. Now, unsaturated fatty acids are going to bend and pack together in a much less ordered way. I don't know why I'm yawning. I apologize. A much less ordered way with greater potential for motion. Okay, so looking at this, again, thinking about basically two different groups of people. If you have any family members who have been, concerned with their cardiovascular health or cardiovascular fitness, chances are that they might eat a diet that is low in saturated fats. So what that means is they're going to avoid lots of animal fats. They're going to avoid bacon. Oh boy, they're going to stay away from bacon. Um, and then they're going to have a diet that's a little bit more rich in unsaturated fatty acids. So they're going to have a diet that has more unsaturated fatty acids than saturated if they can. And so they're going to eat lots of plants because plants have rich sources of unsaturated fatty acids. Okay, now here's the way that I think about it. Or here's the way that I think is helpful to think about it in terms of the packing. So here what we have, I'm going to go ahead and, I'm going to use the tool here. I'm going to use the annotate tool, and I think that I can come up with let's see. There we go. That's what I'm going to do. I'm going to use my arrow, and I'm going to say, all right, arrow, arrow, 3, 4, 5, 6. So we've got 6 arrows wide. Okay. Now I'm going to select those arrows, all of them. Oh, and I'm going to basically say, all right, in the space that these 6 arrows occupied on the left-hand side with saturated fatty acids, I had a total of 5 fatty acids packed in there. Now, considering the same amount of space where these 6 arrows are, when I compare that space to my unsaturated, or my mixture of my saturated and unsaturated fatty acids, how many fatty acids do I have packed in there? I've got 3. So which one of them is more dense and rich with a bunch of saturated fatty acids, or a bunch of fatty acids? It'll be your saturated fatty acids because they cluster so well together. Now, with that in mind, if you're talking about someone who is, an endurance athlete, they run 100 miles a week. Do they need lots of energy? They do. And so having that having a fat adapted diet where they consume lots of fat, small amounts of carbohydrates, um, decent amount of protein, that's a great thing for that person because they need lots of energy in order to fuel their body to not only run 100 miles a week, but to do anything and everything else in their day-to-day life. If you compare that to someone who maybe has heart disease and they by and large are not very active, do they need that same amount of fat? No, they don't. They don't need to ingest that much. And the reason being is because they're not using that much energy. Essentially, it's like they're storing that energy, but ultimately that energy store, it never gets used. So that storage just keeps getting packed and packed and packed and packed. So in the event that you've ever heard someone talking about, oh, I need to eat more unsaturated fatty acids, if that person is an endurance athlete and they run 100 miles a week and they lift weights 4 times a week, that person might be a really good candidate to ingest more saturated fatty acids. And so the unsaturated fatty acids, it might be like, listen, you're running so much that you're burning more fuel than you're taking in. And if you keep doing that, you're going to start depleting muscles and you're going to deplete all your energy stores. So that might not be such a grand idea. Now, with all of that in mind, um, and I think that it's on the next slide. Um, that's just kind of I don't know, not like a stump speech or anything, but I think that that's like a connection to maybe things that you've heard with respect to diet and macronutrient intake and how it relates to molecules at the molecular level or substances at the molecular level. Now, here what we see is a table of common biological fatty acids. What I'd like to draw your attention to is on the left-hand side here, we've got our saturated fatty acids. They range from 12 to 24 carbons. Your most common ones are going to be 16 and 18 carbons long. Saturated fatty acids, no double bonds. So they're going to have 18 colon 0, 22 colon 0. They all have common names in this column. For instance, stearic arachidic acid, behenic lignoceric acid. They also have a systematic name. And this is maybe something that's closer to things that you've heard. For instance, 18 carbons is octa, deca, noic. So octo, or the prefix octo meaning 8, and deca meaning 10, so that's 18 carbons. Tetracosanoic would be, well, 24 carbons. Hexacosanoic, not listed on here, but that would be 26 carbons. So your systematic name has to do with basically prefixes and numbers of carbons. Now, what I would like to draw your attention to is this column right here. This column right here shows our melting points. And so that means the temperature at which we go from a solid to a liquid. Okay, so essentially what that means is this is all measured in degrees Celsius. If room temperature is, let's call it 25 degrees Celsius, and we were to take something like lauric acid, and we said, all right, we're going to incubate lauric acid at room temperature, 25 degrees Celsius. Is lauric acid going to be a solid or a liquid at that temperature? Well, at if lauric acid is at 25 degrees Celsius, that means the temperature that it's at is below the melting point. Okay. So what that means, I guess a parallel you could draw is that's like saying you've got an ice cube at, I'll say negative 15 degrees Celsius. Okay. It's a solid. That ice is frozen. Now, lauric acid here is going to be a solid at 25 degrees Celsius. Not until it hits 44.2 will it begin transitioning to a liquid. Okay, so that's one piece of information to take away from this. Now, to look at that column and recognize a trend, one trend or one thing that I want you to recognize is that the columns, like the bookend columns of this, they kind of match up. What do we see here? On the left-hand side, we see that the number of carbons is increasing as we go down the table. What do we see over here on the right-hand side? We again see that the number is increasing. So if a 12 carbon compound has a melting point of 44.2 and a 24 carbon compound has a melting point of 84.2, what we've seen is the number of carbons going up and the melting point going up as well. Okay, so a way that you could put that is number of carbons, and you could kind of say as the number of carbons goes up, melting point goes up. Next up, unsaturated fatty acids. Okay, so here we've got fatty acids with double bonds. And one thing to keep in mind is you could have a fatty acid with one double bond, with two double bonds, with three double bonds. Really, you have a couple of different options there. Now, one thing that I'd like to draw right off the bat is that we've got a 16 carbon long fatty acid with one double bond. And it has a melting point of -5 degrees Celsius. So what that means is that if you have that palmitoleic acid at room temperature, 25 degrees Celsius, you are above the melting point. So what that means is that is definitely going to be a liquid at room temperature. Now, I'd like to go ahead and, we'll pick out a couple of details here, but the trend remains true. I'm going to pick out a couple select details to illustrate this trend. When we look at 16:1 and 18:1, well, the difference between those is, on one hand, the placement of the double bond, but also the number of carbons. What changes between a 16 and an 18 carbon long molecule is two more carbons. That causes our melting point to go up. So that detail right here remains true. As the number of carbons increases, the melting point increases. Now, let me go ahead and also compare that to, let me go ahead and take this 18:1 and compare that to an 18:2 and an 18:3, making a little E there. 18:1 has a melting point of 13.2. 18:2 has a melting point of -9. And then 18:3 has a melting point of -17. So although there is the trend as the number of carbons increases, the melting point increases, there's also a trend that as the number of, I'm going to label it as DB or double bonds increases, what happens to the melting point? In this case, the melting point decreases. So those two are inversely related. Now that trend is absolutely true amongst all of these. And so if you wanted to kind of crack all those open, that's where you would arrive. Now, what I want you to take away from this is this detail and this detail. Here what we have are 18 carbon long molecules. And what I want to show you, and I want to show you the numbering scheme, the omega numbering scheme. The omega numbering scheme, we're starting from here. There's another numbering scheme known as the delta numbering scheme. And that's where we provide a little bit more detail, where we say delta 9. So this right here is oleic acid, that is delta 9. The difference is that we're starting from carbon number 1. Now, the tricky part about comparing the omega and the delta numbering scheme, the omega or N numbering scheme, is that these two fatty acids, they both are, well, delta 9 and N minus 9. Both are going to utilize the 9 there. Linoleic acid here, or linoleic acid here. Well, this is 18:2 delta 9, comma 12. This tells us where our double bonds are. They're at carbon number 9 and they're at carbon number 12. Now, this is written differently using a omega numbering scheme, and that's because our numbering is starting from right here. So this is going to show up as 18:2 n minus 6 because we start at this last carbon and we count up. We say 1, 2, 3, 4, 5, and 6. That's where we put our first double bond. What's important knowledge to have to understand the omega numbering scheme is that you have to know the sequence of the double bonds, that there is a DSSB or DSSD double single single, sorry, double single single double pattern of those double bonds. Now, here's just one more example. 18:3 n minus 3. Well, our omega numbering scheme starts from 1, 2, and 3. There's our double bond. Now, that kind of wraps our introduction to fatty acids. The next place I want to go is to talk about these molecules known as triacylglycerols or triglycerides. In the event that you get an annual physical, which before too long you probably will begin getting one, when you get that annual physical, they'll do your blood work and they'll check a couple of different things. They'll check your liver enzymes. They'll is your liver function good? And then they will also check for basically cholesterol levels and triglyceride levels, and they'll, basically evaluate, are you at a high, low, or intermediate risk for heart disease or anything of that nature. And what they're going to look for are triglycerides and triacylglycerols, or sorry, fatty acids and triglycerides. Fatty acids, or triglycerides, are basically a fatty acid, but actually one, two, and three of them. Three fatty acids basically linked up to a molecule known as glycerol. So it's basically like you take a glycerol. I always think about this like a Lego. You take a triglycerol, or sorry, a glycerol molecule, and then to that you slap on one, two, three fatty acids, and you make a triglyceride, which is what we see on the far right-hand side here. The most of them contain two or three different types of fatty acid residues. So what that means is you're going to have like one that's a C16, and then you're going to have one that's a C18:1, C16:0, and then finally a C16:2, something like that. You'll have a variation of fatty acid chain length and their number of double bonds. Now, the biological role of triglycerols or triacylglycerols is important. They check for it in an annual physical, but what does that mean? Well, triacylglycerols function as energy reservoirs in humans. That's why, you know, you have tons of energy at your disposal at any given point in time. The fat content of normal humans allows them to survive starvation for 2 or 3 months. Now, I think this is an average number. Um, and I always like to bring up this one guy who, I don't know if anyone ever looks on Reddit. Let me see if I can remember his first name. By that, I'm going to Google him. Um, and there is a there's a story about a guy. I'm going to go ahead and share it, or share my screen there. Actually, what I'll do is, let me see, I'll open the Wikipedia page. There we go. So I'm going to share my screen. This guy right here. This is a guy by the name of Angus Barbieri. He was a Scottish man who fasted for 382 days from 14th of June 1965 until the 30th of June 1966. He subsisted on tea, coffee, sparkling water, and vitamins while living at home in Tayport, Scotland, and frequently visiting Maryfield Hospital for a medical evaluation. He lost 276 pounds and set a record for the length of a fast. So essentially, what his body was doing was it was tapping into those energy reservoirs. He had accumulated large amounts of fat in his body, and it was, they just started to pluck away at it as his body wasn't taking anything new in. It was like, well, we've got some left, so we'll go ahead and utilize this. So that's over a year, which is kind of wild. Um, but there we go. Now, with that, back to our lecture. Um, that fellow avoided starvation. He did it for over over 12 months. Most people allow them, or most people can survive without anything for the better part of 2 to 3 months. But there are exceptions to that. Now, triglycerols or triacylglycerols function to insulate as well. So they kind of serve as like a basically a warming barrier. Now, years and years ago, there was a substance named olestra that was produced. This was a carbohydrate-based fat substitute, and I always like to bring this up kind of as an anecdote because um, this was whenever I think it was in middle school when this came out, um, and this was like I think it was Frito-Lay who developed this fat substitute. And it was kind of like what they did was they made like I guess it was basically it was like a diet chip. It wasn't a baked chip, instead it was a diet chip. And so it was almost like you get Doritos that had like little to no fat content because they use this olestra. And this olestra, what was kind of tricky about it was basically your body got it and was like, I don't know what to do with this. So I'm not going to send it through my normal channels. I'm not going to break it down like it's fat because it's not a fat. And I'm not going to break it down like a sugar because it's not a sugar. Um, and those were pretty big in the market for a while. But then, people started having like really intense GI issues. And so then all of a sudden it was like, well, I like Doritos, but I don't like having horrible bowel movements. So, hmm, the bowel movements are really bad. I think I'm just going to eat Doritos. So they kind of eased their way off the market by, yeah, because of GI issues that were imposed. Now, with that said, triglycerols or triacylglycerols, another context that you've maybe heard of them. If you ever saw the movie or read the book Fight Club, they talk about a process known as saponification. This is the formation of soap from triacylglycerols. Like I said, that triacylglycerols are a great energy store or energy reservoirs in animals, and that's not just people, pigs, cows. Saponification is the process by which or triacylglycerols are used industrially and broken down using. So in Fight Club, they talk about saponification as a way to make soap. And so this is something that isn't done industrially. Um, and essentially what you use is lye or sodium hydroxide to basically break that fatty or like triacylglycerol down and to a sodium fat of a fatty acid or sodium salt of a fatty acid. Now, cholesterol, our next molecule that I wanted to talk about. This is based on a core structure consisting of three six-membered rings fused to one five-membered ring, all fused together. So this right here is cholesterol. Now, this structure is the most common steroid in animals, and it's a precursor for all other steroids in animals. Now, I want to bring this up because this is a lipid. Because if we think back to the very early or very beginning of our slides, we talked about lipids being compounds that were soluble in organic solvents. An organic solvent is lots of carbons and hydrogens, and this goes into solution really well because it is itself a bunch of carbons and hydrogens. Sure, there's an OH group there, but mostly this is carbons and hydrogens. So, cholesterol is an example of a steroid. Now, steroid hormones that you're maybe a little bit more familiar with, your steroid hormones bind to highly specific receptor proteins in the nucleus, and they regulate gene expression and metabolism. So, the ones that you're maybe a little bit more familiar with are your major sex hormones and ones that are produced by the adrenal cortex. For example, testosterone, and maybe if you like watching sports or something, you're maybe familiar with cortisol. That's your stress hormone. Um, Now, that's cholesterol. So whenever it comes to cholesterol, what I want you to know about is I want you to be familiar with that general structure. And then I want you to know that this is the most common animal steroids, and it's a precursor to all of these over here. Testosterone, aldosterone, prednisone, prednisolone. These are good examples of steroid hormones. So these are going to, basically tell different parts of your body to do different things. Now, the last group of compounds that I wanted to talk about are lipid compounds, are lipid-soluble vitamins. Now, our fat-soluble vitamins, or maybe what you might know them as, are A, D, and K. AD, A, D, E, and K. A serves as the site of the primary photochemical reaction in vision. So vitamin A is good for your eyes. Vitamin D regulates calcium and phosphorus metabolism. Vitamin E serves as an antioxidant. It's necessary for reproduction and may be necessary for reproduction in humans. And then vitamin K has a regulatory function in blood clotting. The one that we're going to focus in on is vitamin D. Vitamin D is actually kind of a class, a group of structurally related compounds that play a role in the regulation of calcium and phosphorus metabolism. The most abundant form in the circulatory system is vitamin D3, shown here in the middle. If you've ever heard about vitamin D and talked about vitamin D, one of the ways that you've probably talked about it is with respect to, oh, well, all you got to do for vitamin D is go outside. And you have to get what's known as UV light exposure. Now, UV light exposure is complicated because in places like Central Texas, your UV light exposure is very high. But then in places in the northern United States or in Canada, for instance, your UV light exposure is very low. Now, having UV light exposure be very high, well, then you run the risk of basically leading to certain forms of cancer developing. Whereas if it's too low, then you're not going to get enough vitamin D. So it's kind of a balance that you need to strike. Now, vitamin D, the reason that it has to undergo, or basically um, you have to get UV light exposure, is this molecule right here, 7-dehydrocholesterol, will be broken open. These four rings will basically be, this molecule will be broken, and you'll be left with one, two, three rings. Then there's another processing of this that still leads to a one, two, and three ring structure. So the way that I want you to think about vitamin D is that it starts out with four rings, zapped with UV light, and you're left with three rings. Those three rings are going to, lead to the formation of unique and new compounds. Those new compounds are going to give you something that is then functional. Now, in order for this to work, you have to have a healthy liver and a healthy set of kidneys. Well, kidney. This is the most abundant, or sorry, um, the most abundant form of this in the circulatory system is vitamin D3. Now, that would be cholecalciferol right down here. I'm going to scribble this out and this out. Okay, so there's a lot to cover there with lipids and fatty acids. I want you to know the different classes, and I want you to know a little bit about each of these. I want you to know the fat-soluble vitamins, and basically, the nomenclature, the numbering is really important. I want you to be able to identify something as a an omega-3 or an omega-6 or an omega-7 fatty acid. Um, Other than that, though, I hope that you have a good one. I hope this was helpful, and I hope you learned something about lipids and fatty acids and, well, the different kind of types of lipids. All right, well, have a good one.